Okay, so for naming ionic compounds, we want a system so that you can derive the name from the formula and vice versa. And knowing, first of all, what we need to know is the charge on the ion. And we know for the A group metals, that the charge is equal to the group number. Since ionic compounds involve metals and nonmetals, though, it's a pretty good bet that sooner or later we're going to have to deal with some B group metals. And that means that it's kind of a difficulty that the charges of the B group metals vary, and they're not really very predictable. And many of the B group metals can, in fact, take more than one charge in their compounds. So that can become a little bit of a difficulty. Because so many of the B group metals can take more than one charge from one compound to another, that means that the charge of the metal, if it's a B group metal, has to be specified in the name. If it's an A group metal, the charge doesn't have to be specified because everybody knows what the charge is. If it's in group 1, the charge is +1. If it's in group 2, the charge is +2. If it's in group 3, the charge is +3, and so on. But for the B groups, you can't say that. You don't know what the charges are. You have to figure them out. It's actually also the case, just to make things even a little more complicated, that some of the B group metals, or transition metals, only form ions with one charge. So for instance, silver, which only ever forms +1 ions, zinc, which always forms +2 ions, and in case that's not fun enough, turns out that there are a couple of the A group metals that can take more than one charge. Most prominent among them would be lead, which can be +1 or +2 in its compounds, and tin, which can be +2 or +4 in its compounds. So for lead and tin, you need to specify the charges. For silver and zinc, you don't technically have to, but it's okay if you do. So because these are transition elements, you might want to just stay in the habit of always specifying the charges for transition elements plus lead and tin. Okay, so for naming binary ionic compounds with A group metals, and binary just means 2 elements are present. The name is going to be the name of the cation, which is the name of the element, followed by the base of the anion name ending in IDE. Okay, so for example, we have NaCl, which is sodium chloride. And Al2O3, which is aluminum oxide. So notice oxygen becomes oxide when it's in an ionic compound. Chlorine becomes chloride when it's in an ionic compound. There is a list of base names in the text on page 89, or at least the edition I'm using, down at the bottom of the page. So you can see fluorine becomes fluoride, chlorine becomes chloride, bromine becomes bromide, iodine becomes iodide, oxygen becomes oxide, sulfur becomes sulfide, nitrogen becomes nitride, and phosphorus becomes phosphide. And then here are the anions with their characteristic charges. And so you can check that out. In binary ionic compounds with B group metals, the idea is much the same, but not entirely. So with B group metals, or lead or tin, what you want to do is indicate what the charge on the metal is with a Roman numeral in parentheses right after the name of the metal. And so that is the one difference between naming ionic compounds involving A group metals and B group metals, is you have to indicate, for a B group metal or lead or tin, you have to indicate the charge on the metal ion as a Roman numeral in parentheses right after the name of the metal. Still, the name of the cation is just the name of the metal, and the name of the anion is formed the way we formed them before, the base of the anion ending in IDE. So that stuff should all be the same. So copper with a +1 charge would be named as copper with a Roman numeral 1 in parentheses, copper 1. Copper with a +2 charge would be named copper Roman numeral 2 in parentheses. And there's a list on page 90 at the bottom. Basically the page after that. There we go. This list also gives the older names, and the older names were a real pain in the backside, because in a lot of cases where the symbol is based on a Latin name for the element, the name for that element in ionic compounds was also based on the Latin name of the element, not the English name. So if the compound that we call today iron 2 chloride would have been ferrous chloride by the old system. And you can see how that would get kind of confusing pretty quickly. For one thing, it really messes with alphabetical order. You would expect to find iron compounds under I, but under the old system, a lot of them, not all of them, but a lot of them end up under F, which is a bit of a problem. So fortunately, we don't use that old system anymore. The Roman numeral system You might think that's a pain, but not nearly as much as the old system was. So if you have a compound, what you might have to do is basically figure out from the formula what the name of, or what the charge on the ion is. So for instance, if you had CuCl, we know you have to start with what you know, basically, and work to what you don't know. Copper is a transition metal, so we don't know what the charge on that is going to be off the top of our heads. Chloride, though, always has a -1 charge when it's with a metal. So we know that the overall charge on this compound has to be 0. And we know that chloride is -1. And we can look and see that there's only one copper to bring it back up to 0. So to go from -1 to 0, copper has to be +1. And so this is copper 1 chloride. On the other hand, if it were CuCl2, we could do the same thing. Know that the charge on the compound overall has to be 0. And we recognize that when chlorine is with a metal, it's always got a charge of -1. There are 2 of them, though, so that's -2 for the chlorine part of the molecule. That means the copper part of the molecule has to be +2, and in fact, there is only one copper, so that copper has to be +2. So this is copper 2 chloride. Okay, so that's a look at that. Let's see. Another example might be FeO. It's some sort of iron oxide, but iron is a transition metal, so we have to specify the charge. Knowing that a compound would have 0 charge overall, and also knowing that oxygen, since it's in group 6, will take a charge of 6 - 8, which is -2. So the oxygen part of the molecule is -2. That means the iron part of the molecule has to be +2 to bring it back up to 0. And there's only one iron atom there, so that iron atom is itself +2. So that's iron 2 oxide. On the other hand, we might have a formula Fe2O3. That's another type of iron oxide. But again, since iron's a transition metal, we have to specify the charge. We know that it's 0 overall as a charge. In this case, the oxygen is -2 each, but there are 3 of them. So -2 times 3 is -6. And we know that the iron part of the molecule has to be +6 to bring that up to 0, bring the -6 up to 0. It's +6 - 6 is 0. This time, though, there are 2 iron atoms to share this +6 charge, so each iron atom is going to be +3 each. So this is iron oxide. You can also use the cross multiplication method in reverse, where you make the subscript of one atom the charge for the other. You just have to keep straight that the metal is going to be positive and the nonmetal is going to be negative. If you do that, you find that you end up with iron being +3 and oxygen being -2, which is exactly what we figured out over here. You can do it, again, you can do it either way. The one catch is that in cases like this, where you have a 1-to-1 ratio, you might be tempted to take 1 as the coefficient or the subscript from each of these atoms and cross multiply it, and you'd end up thinking that iron had a charge of +1. And that's why I actually prefer to reason it out like this rather than using the cross multiplying method. The cross multiplying method is easier, but it leads you astray sometimes. So you have to watch out for that. And so now we come to naming ionic compounds with polyatomic ions. Well, polyatomic ions are already ions, so you don't have to worry about changing the name. If there's a polyatomic ion in the formula for a compound, just use the name of the polyatomic ion. So for example, the compound from sodium and the nitrate ion would just be called sodium nitrate. And the formulas for compounds like this would be derived from the charges on the ions, just like they were in the previous examples. Sodium, again, is in group 1. So it will have a +1 charge in its compounds. The nitrate ion, though, has a charge, but the charge is not immediately obvious from the name of the ion. And since polyatomic ions are not listed in the periodic table, you pretty much have to either memorize the charges on the polyatomic ions, or you have to look them up. And if you look up the nitrate ion, you'll find that its formula is NO3, and it has a -1 charge. And because of this, sodium and nitrate will go together in a 1-to-1 ratio, and it would have a formula of NaNO3. In a case like this, where there's only one polyatomic ion in a compound, you just basically write the formula for the polyatomic ion. That's the usual way to do it. Because of this, though, it's easy to mistake the polyatomic ion for just a couple of nonmetal atoms that are part of the compound. And that can be deadly when you're trying to name the compound, for example. So it's important that you be able to recognize a polyatomic ion when you see it. And in fact, if you see a formula with a polyatomic ion in it, it might even make sense as soon as you recognize the polyatomic ion, do something like put parentheses around it so that you'll remember that that part of the molecule is sort of acting as a separate unit. Okay, so if more than one polyatomic ion is present in a molecule, then you should definitely put parentheses around it and put a subscript after the parentheses to show how many of the polyatomic ions there are in the compound. So if you wanted to form a compound from calcium and the nitrate ion, the name would be, unsurprisingly, calcium nitrate. Calcium is in group 2A, so it will form ions with a +2 charge. And the nitrate ion, of course, is NO3 with a -1 charge. And you have the calcium +2 and NO3 -1. Obviously, it's going to take 2 nitrate ions to cancel out the charge on 1 calcium ion. You can also get that result by cross-multiplying And the formula you end up with would be written as Ca parenthesis NO3 close parenthesis 2. CaNO3 2 would be the formula for calcium nitrate. If you look at the list of polyatomic ions at the end, down at the bottom of page, I think it's 91. There we go. Down at the bottom of page 91, there's a long list of polyatomic ions. You'll notice through the list that almost all of them have negative charges, and most of them involve oxygen. The one exception would be the ammonium ion. That's the only polyatomic ion of any significance that actually has a positive charge on it. But again, when you use it in compounds, that means it would be listed before the negative ion. And you just use the name ammonium for it. So if we wanted, say, the compound formed from ammonium ion and chlorine, we would look up the ammonium ion and find that it's NH4+, and chlorine is in group 7, and being a nonmetal, it takes an ion with a charge of group number -8, so that's 7 - 8, which means -1. So obviously these are going to go together in a 1-to-1 ratio, and the formula would just be written as NH4Cl. Okay. If you look at a compound formed from the ammonium ion and the sulfate ion, whoops. The ammonium ion, of course, has the formula NH4+, and the sulfate ion has the formula SO4 2-. Clearly, it's going to take 2 of the +1s to cancel out the 1 2-. And so that means that the formula, you need 2 ammonium ions. So the formula for the ammonium ion has to go in parentheses, while the formula for the sulfate ion does not, because there's only 1 sulfate ion in this compound. So ammonium sulfate would have this formula here. If you had ammonium nitrate, that would be a combination of NH4+, the ammonium ion, and the nitrate ion, NO3-. They go together in a 1-to-1 ratio, and so that would just be NH4NO3. Kind of a long formula, and you do need to be able to recognize that as a combination of 2 different polyatomic ions, but that's what the formula would be. Okay, there is, like I said, a table of polyatomic ions on page 91. There is some systemization of the names for the polyatomic ions. You notice that all of them except ammonium involve oxygen, and they are generally named for the non-oxygen element. So at least the root of the name is based on the element present that's not oxygen. And generally the suffix or the ending ATE is reserved for the polyatomic ion between a given element and oxygen that has the highest possible number of oxygens. And the ITE ending is reserved for the combination of that element and oxygen that has 1 less oxygen. And that is generally true. The problem, the only problem is that you don't really know off the top of your head what is the maximum number of oxygens for a given nonmetal other than oxygen. For phosphorus, the maximum number of oxygens is 4. but for nitrogen, it's only 3. But for sulfur, it's 4. So, how do you figure that out? It's really not very easy to figure out. So it's probably better just to resign yourself to memorizing them. But like I said, there is a bit of a systematic system for oxyanions, that is, anions that involve oxygen. For instance, those involving chlorine and oxygen, ClO3 is chlorate. So you can see chlor comes from chlorine, and 8 means the maximum possible number of oxygens. So not surprisingly, ClO2 is chlorite. Okay, so far so good. Unfortunately, it turns out there's also an ion that has the formula ClO minus, one less oxygen than the one that ends in ITE. Okay, great. Now what do you do? Well, what they did is they added a prefix to the ion name and made it hypochlorite. Hypo meaning below or less than. So hypochlorite has 1 less oxygen than chlorite. But you're not done yet, because it turns out that there's also a polyatomic ion with chlorine and oxygen that has the formula ClO4 minus. Well, they already used chlorate, and implying that 3 was the maximum number of oxygens possible with chlorine. So what do you do now that they found out that there's one with 4? Well, what they did is they used the prefix per chlorate. Per meaning is from a Latin word that means beyond or through. And so perchlorate means beyond chlorate, 1 oxygen beyond chlorate. Okay, so that's sort of an overview of naming with polyatomic ions. I see here that we're coming up against the limit for this lecture, so rather than running up the clock and getting even further ahead, I think I will end it there, and we will pick up in the next lecture with the rest of this section, which starts with hydrated ionic compounds. And we can go on from there.